Welcome, beginner Unity developers, to an essential guide on optimizing your game's performance. Today, we'll explore why instantiate and destroy operations can be costly in Unity 3D. These fundamental methods are crucial for creating and removing game objects dynamically, enabling interactive game environments. However, frequent use can significantly impact your game's efficiency. Understanding the underlying reasons for this performance hit is vital for building smooth, optimized Unity games. We'll delve into the technical details behind these operations. Let's begin by examining the core reasons why instantiate and destroy can be performance intensive. The first major factor is memory allocation and deallocation. Each time instantiate is called, Unity allocates new memory for the game object, including its components, meshes, and textures. This process is not instantaneous. Conversely, destroy deallocates this memory, returning it to the system. Frequent allocation and deallocation can lead to memory fragmentation. Memory fragmentation occurs when memory becomes scattered, making it harder for the system to allocate contiguous blocks, which can slow down subsequent operations. Another significant factor is garbage collection. Unity employs a garbage collector to automatically reclaim memory no longer in use. When destroy is called, the associated memory is marked for garbage collection. However, the GC runs periodically and can cause performance spikes. During a GC cycle, the game often pauses to identify and free up memory, leading to noticeable frame rate drops or stutters, especially with excessive instantiate and destroy calls. Beyond memory, there's also object creation overhead. Creating a new game object involves more than just memory allocation. The engine must copy data from the prefab, initialize components, update transform hierarchies, and register the object with various systems like rendering and physics. These steps add to the CPU overhead, impacting performance, particularly on lower-end devices where resources are more constrained. Finally, Unity's hybrid engine architecture contributes to the overhead. Unity combines C# managed code with C++ native code. Instantiate and destroy operations require interaction between these managed and unmanaged parts, introducing additional overhead due to interop. Now, let's see these performance impacts in action. We'll demonstrate this using code examples in Visual Studio and the Unity Profiler. Here, we have a simple C# script in Visual Studio that repeatedly uses instantiate and destroy to create and remove game objects. We'll use loops to create a large number of objects and then destroy them, simulating a high-stress scenario in a game. Next, we'll switch to the Unity Profiler to measure the real-time performance impact of these operations. This tool is invaluable for optimization. The Profiler provides detailed information about CPU usage, memory allocation, and garbage collection, giving us a clear picture of what's happening. Observe the CPU usage as we run our script. Notice the significant spikes when instantiate and destroy are performed frequently. These spikes indicate moments where the CPU is heavily burdened, directly impacting your game's frame rate and responsiveness. Now, let's look at memory allocation. You'll see the amount of memory being allocated per frame increasing rapidly. High allocation rates are a red flag, as they often lead to more frequent garbage collection cycles, further degrading performance. The GC statistics in the profiler will show how often the garbage collector runs and the time it takes to complete its task. Each GC event represents a potential stutter in your game, especially if it takes a long time to collect memory. Finally, observe the frame rate drops. When instantiate and destroy are used extensively, the frame rate visibly plummets. This visual demonstration clearly illustrates the performance impact, making your game feel unresponsive and unpolished. To further illustrate, we've set up a scene with a script that spawns and destroys objects, like bullets or enemies, at a controlled rate. A UI element allows us to adjust the rate of spawning and destruction, and the frame rate is displayed on screen in real time. As we increase the rate, you can see the frame rate drop significantly, confirming the performance cost of these operations. Now that we understand the problem, let's explore helpful tips and best practices to mitigate these performance issues. Object pooling is a powerful solution. Object pooling is a design pattern that significantly reduces the overhead of instantiate and destroy by reusing objects instead of creating new ones. Instead of destroying objects, they are simply deactivated and stored in a pool. When a new object is needed, it's retrieved from this pool, activated, and reused. This approach completely bypasses the costly memory allocation and deallocation processes, leading to much smoother performance. To implement object pooling, you can create a generic script that pre-instantiates a certain number of objects and stores them in a list. This script would provide methods to easily get an object from the pool when needed and return it when it's no longer active. Let's see an example with a bullet system. Instead of instantiating a new bullet each time the player fires, we get one from the pool. When the bullet hits a target or goes off screen, it's simply returned to the pool, ready for its next use, avoiding destruction. Another simple yet effective tip is to deactivate objects instead of destroying them if they might be used again later. Deactivating an object is significantly faster than destroying and then instantiating it again, as it avoids memory operations. It's also crucial to limit the frequency of instantiate and destroy calls. Avoid performing these operations in every single frame. If possible, group these operations or perform them less frequently. For instance, spawn enemies in batches rather than one at a time. Optimizing memory usage is another key strategy. Reduce the memory footprint of individual game objects. This includes using texture compression, reducing mesh complexity, and avoiding unnecessary components. Smaller objects are faster to instantiate and destroy. Beyond these core practices, several additional tips can further enhance your game's performance. For static objects that don't move, utilize static batching to reduce draw calls. This groups multiple static meshes into a single batch for rendering. When rendering many instances of the same mesh, GPU instancing is highly effective. It allows the GPU to draw thousands of identical objects with a single draw call. Occlusion culling prevents the engine from rendering objects that are not visible to the camera, saving significant rendering resources. This is particularly useful in complex environments, ensuring only what the player sees is processed by the rendering pipeline. Finally, consider asynchronous loading for assets. Loading large assets can block the main thread, causing hitches. Asynchronous loading allows assets to be loaded in the background without freezing the game, providing a smoother user experience. By implementing these tips and best practices, beginner Unity developers can effectively manage the performance impact of instantiate and destroy. You'll be able to create smoother, more efficient games that provide a better experience for your players. Remember, understanding these core concepts is the first step towards becoming a proficient Unity game developer. Keep experimenting, profiling, and optimizing your projects. Your players will thank you for it.